Bismillahirrahmanirrahim. Today I try to explain some more practice questions on Fourier series. Last time we see how to solve the Fourier series question in an interval 0 to 2 pi, but here we are talking about some periodic intervals, that how we can solve a question that is expanding in a periodic interval. Here the Fourier series of a function is defined on the interval minus p to p is defined as this topic I am taking from DJ Zil book, that's why I am telling you. Here we know that this is called the Fourier series. F of x is equal to a naught plus summation 1 n is equal to 1 to n is equal to infinity a n cos n pi x over p plus b n sin n pi x over p. Here you know that this a naught, a n and b n are called the Fourier coefficients. These are called the Fourier coefficients. I am explaining here. Now the values of these constants are a naught is equal to 1 over 2p from minus p to p f of x dx. In the last lecture I do some mistakes there in writing, in typing there. I'm writing here 2 pi, but the formula is 2p. The formula is 2p. So kindly you correct yourself in the previous lecture in when I am introducing such type of coefficients there. Here the value of a n is 1 over p minus p to p f of x cos n pi x over p dx. And the third one is p n is equal to 1 over p minus p to p f of x sin n pi x over p. Now we see some problems over periodic intervals. Here the first example I have taken from that book, that is expand f of x is equal to, this is a piecewise function, 0 which is defined in the interval minus pi to 0, and the other value of f of x, that is pi minus x, that is defined from 0 to pi. You see here this is the periodic interval. This is the periodic interval minus pi to pi in a Fourier series. Now we move toward its solution. How we can define its solution is, here the interval is minus p to p, that is it is clear from here that minus pi to pi, so you write here minus pi to pi. With when you open this, how you can open this? You subtract the initial value from the final value. I am writing here p minus p is equal to pi minus pi, so it becomes 2p is equal to 2 pi. When 2 is cancelled with this 2, after simplification we get p is equal to pi, so we get the value of p is pi. Now we move towards its coefficients. How we can find the coefficients of this Fourier series of this question in the form of Fourier series, and we know that the formula of a naught is equal to 1 over 2p minus p to p f of x dx. Here I am substituting the value of p here. At the value of p I am writing here p pi, then from minus p, that from minus pi to p, that is pi f of x dx. Now I expand this interval, or I split this integral over the intervals. First I am writing minus pi to 0, and in this interval the value of the function is 0, plus then I write from 0 to pi, and in this interval the value of the function is pi minus x. So this implies that 1 over 2 pi, this value becomes 0, and this is, and I again split this interval, split this integral 1 through minus pi and then for x. Minus pi is constant, I am taking outside, so it's from 0 to pi dx minus 0 to pi x dx, and 1 over 2 pi after integrating this I get pi square minus, and after taking its integral and substituting the limit, I get pi square over 2. And when I simplify this, I get pi by 4. So now we move towards the second Fourier coefficient, that is an. Its value is 1 over p minus p to p f of x cos n pi x over p dx. And you see here I am substituting the value of p, that is pi again here 1 over pi minus pi to pi f of x cos n pi x divided by pi. This pi is cancelled with this pi. After simplification we get cos nx. So you see here 1 over pi from minus pi to 0. I am splitting the integral along the interval minus pi to 0. In this interval you know that the value of the function is 0, cos nx dx, plus then from 0 to pi the value of the function is pi minus x cos nx dx. Here you see an is equal to this value, this integral becomes 0, and after this I split this interval, split this integral over pi to minus x. 1 over pi into 0 to pi cos nx minus 0 to pi x cos nx dx. If you remember the previous information from the last lecture, that I am telling you, when a cos or sine, when I am taking integral of this, it becomes sine n of x divided by n. And you see here, when I am taking its integral, it becomes sine nx over n. Okay. And you see here what are its limits, that is 0 and pi. Here you have sine. When you evaluate sine at pi, the value of sine at pi is equal to 0, and similarly the value of the sine at 0, it is equal to 0. So this total term become 0. So I am now writing below here. Here we have minus 0 to pi x cos nx dx. You see here you have two terms here, one is algebraic and the other is trigonometric here. So we use by parts formula here. I am taking this negative outside, that is minus 1 over pi. Then first as it is, integral of second sine nx divided by n from 0 to pi, then minus integral of cos nx is equal to sine nx over n, and the derivative of x is 1 dx. And again you see here the value of sine at pi is equal to 0. So when you substitute 0, it is again equal to 0. So this term again vanishes. So we have only remaining term, that is minus 0 to pi sine nx divided by n dx. You see here, when I take this negative, you have minus, this minus, and when you take the integral of this sign, it again gives us minus cos nx divided by n, minus cos nx divided by n. So the negative of this cos, this negative and this negative, you have three negatives here. On multiplying here you get a negative sign, 1 over n square. Here you see when you integrate this you get minus cos nx divided by n. N is already here, it becomes n square. So I take this n square outside, it becomes n square pi cos nx from 0 to pi. This is equal to 1 over n square pi. When I substitute, when I evaluate this value at 0 and pi, it becomes cos n pi minus cos 0. And you see here, by using De Moivre's theorem, you know that this may write in the form cos pi raised to the power n. This cos pi raised to the power n, and you know that cos pi is equal to minus 1, so it is minus 1 raised to the power n. When I multiply this negative sign inside, so this term become positive and this term become negative, and you know that cos 0 is equal to 1. So it becomes minus 1 raised to the power n minus 1. When you multiply this negative sign inside the parenthesis, the order of these terms reverse. So it becomes 1 minus minus 1 raised to the power n divided by n square pi. In this way, we find Bn is equal to 1 over p from minus p to p f of x sine n pi x over p dx. When you substitute here, the value of p is 1 over pi from minus pi to pi f of x sine n pi x over pi dx. And you know that from minus pi to 0, the value of the function is 0, so I am ignoring that part because it becomes 0, so I take that part which is not 0. So you see here is from 0 to pi minus x sine nx. Again it becomes split into two integrals, and I'm writing here, simplify this as we done above, we get. So it becomes Bn is equal to 1 over n. So you solve this part, and if you get 1 over n, it means your answer is right. If you not approach to this answer, it means there is some problem, and you send me that picture through WhatsApp to me, and inshallah ta'ala I will tell you your mistake and you make it its correction. Hence the required Fourier series is, now I am substituting their respective Fourier coefficients values here. F of x is equal to pi over 4 at the place of a naught plus summation n is equal to 1 to infinity, and at the place of a n I am writing here 1 minus minus 1 raised to the power n divided by n square pi into cos nx plus 1 over n sine nx. Here in the formula you see here cos n pi x divided by p. When you substitute the value of p here, that is pi is cancelled with this pi, and you get only this simplified form. Cos similarly in sine u also. So in this way our first examples comes to end, and then I take second example. As you know that compiling on computer is a very difficult task, and it consumes a lot of time. So I solve question manually here and take its PDF and paste here. So I take first question of exercise 12.2 from the DJ Zeal book, Advanced Mathematics. That is f of x is equal to 0 to 1 from minus pi to 0 and then 0 to pi. There are different values of the functions. The first value of the function is interval from minus pi to 0, and the second value of the function that lies in the interval 0 to pi. Again in the same fashion, I take the interval from minus p to p, its value is minus pi to pi, and after simplification you get p is equal to pi. So the Fourier series is f of x is equal to a naught plus summation n is equal to 1 to infinity a n cos n pi x over p plus b n sin n pi x over p. And you know that where a naught is equal to 1 over p, 1 over 2p minus p to p f of x dx, and similarly the value of a n you know that, and similarly the value of bn also. Now we find the solve the first coefficient. A naught is equal to 1 over 2p minus p to p f of x dx. Here you see that I am substituting here the values of p, and it becomes 1 over 2 pi minus pi to pi f of x dx. Now I expand this integral over the given intervals, that is equal to 1 over 2 pi from minus pi to pi first, and in this interval the value of the function is 0, and the other integral is interval from 0 to pi, and here the value of the function is 1 dx. So this becomes 0, and when you integrate this you get x from 0 to pi. After simplification and evaluating at the limits, you get 1 over 2. Similarly, I take the second coefficient, that is a n 1 over p from minus p to p f of x cos n pi x over p dx. Similarly, I substitute here, you see the value of p here, then you see here 1 over p. Again I splitting the divide the integral according to the given limits, in the first limit and in the second limit. This vanishes, and you have 0 to pi cos nx dx, and when you integrate this it is equal to sine nx divided by n, and you know that at the value at pi sine vanishes, and when you check this sign at 0, it is also 0. So total value of this coefficient is 0. It means there is no wave generated at this node, at this point. So now we take Bn 1 over p from minus p to p f of x sine n pi x over p dx, 1 over pi, again I substituting the value of p here, and then again I split the integral over the given intervals. Here you get minus pi to 0. At this in this interval the value of the function is 0, so it becomes 0. So other has 0 to pi sine nx dx. When you integrate this you get minus cos nx divided by n from 0 to pi. When you check this, minus 1 over n pi cos n pi minus cos 0, and cos pi whole raised to the power n minus 1 by using De Moivre's theorem, and you know that cos pi is equal to minus 1, so it is minus pi raised to the power minus 1 raised to the power n minus 1. And after simplification, when you multiply this negative sign, it reverse its order, the terms the order of the terms, it becomes 1 minus minus 1 raised to the power n. And in this way our required Fourier series is f of x is equal to 1 over 2 plus summation n is equal to 1 to infinity, and you see here you see in the above that the value of a n is equal to 0. So I am not writing that, and only write those which have value. So I have the value of bn here. I am writing here bn and sine n pi x divided by p. When I substitute the value of p, that is pi is cancelled with this pi, so it becomes sine nx. And when you try to draw the graph of this function, here you see that is minus pi, here pi, and you see that in the question from minus pi to 0 the value of the function is 0. So I am draw a line parallel to this. It means there is no wave generated here, there is no digital wave here. And when you see from 0 to pi the value of the function is 1, it means from 0 to pi there is a signal that has value constant that is equal to 1. In this way you can also draw a different graph, and if you feel any problem, if first you draw that and then you send me by WhatsApp, that I check and send you back. It is either it is right or wrong. Now we move towards question number 5. F of x is equal to 0 to x square minus pi to 0, then from 0 to pi. Again the given interval, and in the similar fashion I find the value of p here. Then I write the Fourier series here. F of x is equal to a naught summation this, and you also know that the value of a naught, a n and b n. And first we find the value of a naught here, that is 1 over 2p from minus p to p f of x dx, that is equal to you see here in this question, as you see in the first interval the value is 0. So in the remaining parts of this question I am totally ignoring this part, because in this interval the value of function is 0. Just I am taking only this interval. I am taking only this interval. So you see here when I am expanding this from minus pi to pi, when I am expanding from minus pi to 0, its value is 0, so I am not writing here, and just I am writing only from 0 to pi, and the value of the function here, that is x squared dx, and after simplification you get 1 over 2 pi x cube by 3 from 0 to pi, and 1 over 6 pi when you make substitution here or evaluate the value at the given limits, and you get pi square over 6. Similarly, when you move towards an, it is again 1 over pi from minus pi to pi f of x cos nx dx. Again I am splitting the interval and taken that value which is not 0 from 0 to pi x square cos nx, and so you see here Here is one is algebraic term and the other is trigonometric term, and we use by parts. And you tell me how many times we integrate this. How many times we integrate this? We integrate this only. We integrate this 2 times because which function we have taken as a first function, that is algebraic, and its power is 2. That the function which is taken first, you have to see its power. How many times its power is, you have to integrate by parts at that according to the power of the first function, according to the power of the first function. So you have you see here its power is 2. It means you have integration by parts, apply integration by parts 2 times. So when after integrating this by parts 2 times, I'm letting its final answer here, 1 over pi 2 pi over n square minus 1 raised to the power n. 2 over this pi is cancelled with this pi, and 2 over n square minus 1 whole raised to the power n. I perform by parts, integration by parts here, and lastly I'm writing here its answer. You do its integration by parts by yourself, and if you get this answer, it means your answer is right. If you are not able to reach up to this answer, it means there is some problem. Take its pic and send to me by via WhatsApp, then I will tell you where is your error. So in the last here we have bn is equal to 1 over p minus p to p f of x sine n pi x over p dx. Again I am writing the value of the interval over that interval in which the function is not equal to 0, 1 over pi from 0 to pi x squared sine nx dx. Again I perform here 2 times integration by parts, and I'm writing here its final answer here, 1 over pi minus pi square minus 1 raised to the power n divided by n plus 2 over n square minus 1 raised to the power n minus 1. And you see here this negative 1 I'm writing here as pi square into minus 1 and then minus 1 raised to the power n over n plus 2 over n cube minus 1 raised to the power n minus 1. This negative 1 and this negative 1 raised to the power n, bases are same. Use the results of exponential functions here. Bases are same, so powers add. So in this way I am writing here pi square into minus 1 raised to the power n plus 1 divided by n. So equivalently you also write this in this form, 2 over n square minus 1 raised to the power n minus 1. So hence our required Fourier series is, I'm writing here, and then I substitute the values of their respective Fourier coefficients. In this way this lecture comes to end. Inshallah Ta'ala, one more question that is I think it is complicated. I'm try to solve this and give you understand you in the form of a lecture, and now this you are able to solve 1 to 6 or 7 questions here, and these questions I am sending you in a picture form after some time. That time, okay, take care, Allah Hafiz.